Welcome. You are about to view a recorded talk of the Mathematical Consciousness Science online seminar series held in 2020. This seminar series aims to explore the role of mathematics in the scientific study of consciousness and hopes to connect researchers who have an interest in this topic. While every session of the seminar consists of a talk and discussions, the latter are not recorded and the following will only contain the talk. We hope you will enjoy it. For further information, please visit our website, seminar.math-consciousness.org.
I accepted this invitation to talk about consciousness because I've done a few works related to that. But of course, I'm not a neuroscientist. I'm not a philosopher. Consciousness has not been sort of a main topic of investigation in my life. So I'm coming here with, in a very humble way, just offering a few small contribution from my own discipline, which is physics, of course. So it's three small considerations which, as a physicist, humble mechanician, I can offer to this marvelous, beautiful problem, which is understanding consciousness. These are in a few papers and in a forthcoming book also, which I've written in the last years. And I think their works, I think that they were relevant in one way or the other to the vast issues of understanding consciousness, and there are three. So this presentation, it's gonna be dense in the sense I'm not presenting you a single idea of a single mathematical construction, a single suggestion, but three. On the other hand, I'm not gonna go into details of any of these three. Because if the aim here is just to communicate to you the main idea, and then if you're interested, you can go to see the papers to see how it actually works in the details. I hope to give you the sense of what is the point in each one of these three. The first is has to do with time orientation. Somehow, how a physicist can how physics can deal with the obvious time orientation of consciousness as a process, the openness of the future. The second has to do with meaning. Our mental life, let me put it this way, we understand it using in an ubiquitous way, the notion of meaning. And so there seems to be a difficulty to connect meaning with the physical world. That's what I'm going to talk about. And the third one, I'm going to touch an issue which is called much discussed, which is whether quantum theory has anything interesting to say about consciousness, and offer to you a perspective which I've not seen yet, which is neither, yes, we understand quantum mechanics with consciousness, we understand consciousness with quantum mechanics. I know there is a number of works in that direction. It's not that. Neither, forget quantum mechanics, has nothing to do with it. So I'll get to that. And on the right of the slide, there are the papers where this is discussed. I'll flash them again in the next at the end of the talk. All right. So before starting, let me declare. Let me sort of unveil and open my religion, my politics. Let me tell you if I'm for Biden or for Trump. So because I believe it's things are clear if we declare where we stand from intellectually. I'm not trying to convince you, of course, but I know there is a variety of opinions, but here is where I am, and in a sense, this motivates everything that follows, and everything that follows is in this context. I do not share at all the feeling that consciousness cannot be understood in the context of non-physical laws. Non-physical laws, I really mean the non-physical laws. I mean the whatever, standard model, general relativity, classical mechanics, quantum mechanics, as we have it. I've been curious about the discussion of consciousness for years. I've been reading and following, and I know that among also the people who talked at this series, there are people who disagree with that, and I've been following in detail all the argument of that. I know I've been reading Nagel and Chalmers and everybody else, and I'm not convinced by those arguments. I'm not going to enter into those arguments at present, of course, is a huge philosophical discussion. But I see no reason whatsoever for which this, whatever we mean by consciousness, and of course, people mean different things about consciousness. Whatever we mean by that, the subjective perspective or whatever, I'm not convinced that there should be something that prevents us to understanding it unless we sort of enlarge, go out, or whatever, in one sense, on the actual physics that we know. So this, of course, does not mean that we understand how consciousness works, of course, but there are many things we don't understand in the world. We don't understand thunderstorms. If you ask for a person studying meteorology, there are a lot of open questions about thunderstorms, and but nobody suspects that to understand thunderstorms, we have to change something fundamental in our physics or in our philosophy or something like that. So in other words, I think that there is no hard problem of consciousness, the terminology of David Chalmers. I do think there are no zombies. But of course, in the terminology of Chalmers, what he calls the easy problem of consciousness is extremely hard. So the easy problem of consciousness is probably the most misleading definition of an expression in the history of thinking. It's a very hard problem, and it raises some very surprising questions, precisely because the phenomenon of consciousness has features that prima facie seems to clash violently against the physicalist reading of the world. And this is exactly where I'm giving a contribution as a physicist. So I'm addressing these strong clashes and say how, as a physicist, one can react to that. And again, these are the three contributions I'm gonna give. The first one has to do with one of the aspects of the phenomenology of consciousness, which is agency, the possibility of taking decision, acting on the future, and therefore of giving an understanding of the world in which the past is fixed, the future is open, and a conscious agent decides to go right or to go left. How does this square with the physical picture of the world, and in particular with well-known time reversal invariance of fundamental physics? And I'm going to discuss that and argue that it squares very, very well. It makes perfectly sense. It not only makes perfectly sense, but it allows us to trace the kind of informational notions which are relevant in biology and in understanding how mental things work, down to notion of physical notions. The second is, I said it's about meaning, and the third is about quantum mechanics. Again, about quantum mechanics, I'm going to say that the quantum understanding of the world helps us diffusing a strong sense of incompatibility, which is between the mental and the physical, in a way which I will argue doesn't require at all some version of panpsychism or anything like that. All right, so this is just initial blah blah blah. Let me go to business and start from the first point, which is agency. And here we are. So point number one, the source of time orientation of the agent. And what is the problem? Problem is it's simple. First of all, consciousness, I think in a way, I mean, we need a lot of work for understanding consciousness: mathematical work, modeling work, neuroscientist work, philosophical work, physics works, of course, all sorts of things. I believe that at the end of the day, we are going to understand consciousness more as a process than as something that you understand at a single moment of time. Perhaps this is my physicist upbringing and education. In physics, so many times in the history of science, we got stuck. I mean, since antiquity, trying to understand something as a pattern, and we only understood it as a pattern in time, as a process, as an evolution. I mean, when people try to understand the solar system, they understood it as a dynamical thing, not as a static thing, and so on and so forth. So consciousness is a process, it's something that happens, and definitely happens in time and in a time-oriented way. It's an extremely irreversible process in physical terms, right? We are being in time, if I can use even a Heideggerian expression here. We as subjects of consciousness exist in a time-oriented way. Where does this time orientation come from? I'm specifically talking about the orientation, the difference between the past and the future, the thing that allows us to take decision about the future, but not to take decision about the past. Where does it originate, given that fundamental physics is invariant under time reversal, make no distinction between past and future? Well, said like that, it seems a great problem, but in fact, it's a problem that has nothing to do with consciousness. If you just think a moment, because the macroscopic world, it's full of oriented phenomena. In fact, the large majority of phenomena that we see in the world, it's time-oriented. We almost only see reversible phenomena in the world, right? If I take a pencil and let it fall down, it stops on the floor. I never see the pencil jumping up from the floor by itself. So macroscopic physics is time-oriented, all right? So there's nothing funny in consciousness in being time-oriented, because all macroscopic phenomena are time-oriented. We just have to remember how macroscopic phenomena can be time-oriented in spite of the time reversal invariance of the microphysics, and we have the first ingredients for then trying to understand the time-oriented of consciousness. However, I'm going to go ahead, but let me pause here for an observation, because this is absolutely fundamental for thinking about consciousness. Hence, this seems to say very strongly that consciousness is a macroscopic phenomenon, right? It's macroscopic. I'm a physicist. It's macroscopic phenomena which are time-oriented. Okay, elementary phenomena are, in physics, elementary natural phenomena are never time-oriented. In other words, time orientation, it's a feature of the macroscopic description of something. Which means that consciousness being time-oriented, it's an indication, and in fact, from a physicist point of view, an extraordinarily strong indication that consciousness as a phenomenon is a macroscopic description of something. And that's a major point, in my opinion. I'm going to come back to, at the end about that, because I think our intuition about consciousness is deeply misled by the integration of consciousness, by the simplicity of the subjective point of view, by the idea of that it's a single thing. It's simple. It's not simple. It's complex. All right. So consciousness is a macroscopic phenomena. Now, how come that macroscopic phenomena are time-oriented if the microphysics is not? So, well, we understand that very well. That's uncontroversial and clear in the foundation of statistical mechanics. We need two things. One thing we need is indeed a distinction between macro and micro, which means that you have a physical system with variables, and you can give a microscopic description, meaning a description that keeps into account every single variable which is relevant for the dynamics. Or you can give a macroscopic description, which is you give a description in which you ignore a large number of small degrees of freedom, right? entropy comes immediately once you have this distinction, because for a given assignment of value to the macro variable, you can essentially count how many microstates there are, and that's what entropy is. Now, this is necessary for having time. Orientation is not sufficient, obviously, because you don't break symmetry just by changing variables. Something else should break the symmetry between past and future, and it does. And that's the second ingredient you need to have time orientation, which is a contingent fact about our world, which happened to be true, which is that given macroscopic description that we use, because we interact with a small number of degrees of freedom of the units, we don't see the individual molecules in the air. When my pen falls and stops, I don't see the individual molecules heated on my hand. So in this macro description, it is a contingent fact that the entropy was low in the past. Call this past hypothesis, like David Albert likes, call it the fundamental assumption of thermodynamics, that the universe in the past is characterized at every level, cosmological, in our life, in for the biosphere, and so on and so forth, is characterized by the fact that if you go back in time, the entropy is it's lower. Of course, this opens a can of worms and all sorts of problems, if you want, because you might take it as a low God-given thing. The world is like that, like David Albert asked us to do. Or you might ask, well, maybe we can understand that, and there is a story that justifies that, and there are many ideas around. They're beautiful. I like one of these ideas, but that has nothing to do with consciousness. As far as consciousness is considered, it's a fact that the entropy was low in the past, whatever its source and reason. All right, so we have a framework, but this is just a framework. Then the question is, how is it possible that given a physical world where entropy was low in the past, agency comes out? So this opens a question and not closes it, right? How is it possible that just because the entropy was low in the past, and maybe some other ingredients, which I'll introduce in a moment, agency come in? You can decide the future and not the past. And that's where I gave a contribution in recently. In fact, I came there from an analogous problem, which is why we have memories of the past and not memories of the future. Why we, more general, memory is a special case of the fact that there are traces of the past and there are not analogous traces of the future. The only answer is because of entropy. But how is it possible that low-pass entropy creates a macroscopic history where there are traces of the past and not of the future, right? A step in the sand, it's because somebody walked in the past. A crater on the moon is because a stone fell in the past. There should be a story that just from low entropy in the past, you have traces of memory of the past, not the future. And similarly, once this was clarified and understood, it turned out that exactly the same story essentially explains why there can be agents that decide the future, but not the past. So it is the thing to be answered is the following. The second law of thermodynamics, so the growth of entropy plus the past hypothesis, should give us a way, should imply that there can be time-oriented agents behavior, and should imply that the future is open. What the story that connects? What is this flash here? So let's put a little bit of meat in this. What is an agent that decide? Well, it's something that happens at some time, some system that acts at some time, such that the past macroscopic history is the same, but the future macroscopic interest can be different, branch. I can decide to go right, to go left, or to go straight. And so if Qi here are macroscopic variables, I labels the different branches here, 1, 2, 3 here. In the different branches, the macroscopic variables are all equal for a time before some initial time, say here, but they're different after some time TB. And between TA and TB, something happens where the system chooses we're going up, left, right, or straight. Now, question, is this in contradiction with time reversal microscopic physics? Answer, strong and loud and clear, no, it's not. Okay, and let me make a parenthesis here. I could say all that in quantum mechanical terms. It would be much more intricate because you have to talk about probability and so on and so forth. But it would be exactly the same as ignoring quantum mechanics and say it in classical terms. So let me ignore quantum mechanics to avoid entering into complicated talking and just talk classically. Classically, the microphysics is deterministic. Deterministic and time reversal invariant. So the claim here is that this macroscopic behavior does not contradict the microscopic time reversal deterministic invariance. Why doesn't? Well, it's pretty obvious if you think for a moment, because think what happens before the time TA when there is a unique history. This is a unique macroscopic history, which of course includes a large number of different, in fact, a huge number of different microscopic histories. So nothing, it's strange if some of them go right, some of them go left, and some of them go straight. So the branching is just the fact that the microscopic histories go in different directions. This is the possibility of branching for the macrophysics. And I just want to mention that, I'm going ahead, this is just the first step. I want to just mention that when my paper came out in 2020, quite surprising in philosophy very lower, came out with a description of agency and free will, which is basically exactly the same idea. And in fact, the idea is not so surprising at all. It's very old, and it's exactly the standard solution of the free will problem in Spinoza. If you look at the Ethics, and the last book of the Ethics is very last book of the Ethics is very clear. Freedom of the agency is the result of the macroscopic approximation. And let's be more precise here. The macroscopic story makes sense because to some extent it is causally close. You can give a causal story of what happens. So before the time TA, the macroscopic evolution, let's suppose we have some dynamical theory that tells what happened, and so after the time TB. In between, the macroscopic dynamical story breaks down because there's agency, because somebody chooses freely. But of course, there's nothing strange if it breaks down because it was an approximation, right? So what is agency is the boundary of the causal closure of the approximate description of what is going on. Now, let's make this, to understand what is going on and introduce we need to understand that. Let me illustrate a simple sort of physicist way of thinking here. A very simple system that models what is the central aspect of the story here. Imagine a box in which we have two physical systems. One is a sort of hot system. There's a lot of little orange balls moving very fast. And we give a macroscopic description. We don't know the position of each one of them, but we have an estimate of their average velocity, and therefore they have a kinetic energy, which is to say the temperature. Then suppose they move fast. But then there is a second system, which is those penduli up there, which are a finite number, so the number of them, and we see them moving. So there's some macroscopic energy associated to that, the amplitude of the oscillation. And let's say, that's the point, that at some time in the past, the entropy was low, namely there was no equilibrium, namely the energy in the pendula is lower, the temperature of the average kinetic energy of the pendulum is lower than the average kinetic energy of the fast moving balls. So there is a temperature difference to start with between a hot system and a cold system. That's hypothesis number one, it's past low entropy. And I want two more ingredients. And the key point is that these two more ingredients are sufficient to give agency. In fact, they're also sufficient to give memory. What are the two additional ingredients? One is that the interactions between the hot and the cold is small. So the thermalization time, it's long. There's a long thermalization time. Suppose the ball is the room is very large, so the collisions are rare. So when there is a collision, a little bit of energy goes from the hot system to the cold system, but it takes very, very long time before you get thermalization. That's first assumption, additional assumption. And the second additional assumption is that the thermalization time among the penduli, it's also long. So the penduli, say, are coupled to one another through the air in the room, through the oscillation, the string on which they oscillate, and so on and so forth. So they do share energy, but it takes long. So they have a long thermalization time. And this is not the typical situation of physics books thermodynamical example, but is a typical situation in the world. The world is full of systems which are separated, have different temperatures, and have very long thermalization times. Now, if you have that, what happens? Well, take the energy of the ball. The index I here, it's labels the different penduli. And as I said, initially they all have small energy, but then one of the small orange ball, hot ball, hits one of the penduli. So one of them becomes different from the other. Which one? Well, it depends on which is hit, and which is hit, it depends on microscopic variables. So the macroscopic evolution branches, right? And this happens every time there is interaction. Say there is an interaction every time at all. So we have exactly a branching of the microphysics determined by the microphysics. Okay. Now let's put a little bit of mathematics here. We have, if we know the thermalization times, okay, and the two different temperatures, and the heat capacity, then we can compute the change in entropy of a single collision, of a single act here of choice between which pendulum is being excited. And it's a simple calculation. The change in entropy is given by standard thermodynamics, and the amount of energy exchanged, I can compute it just from knowing from the thermalization time, because it tells me how long it takes for energy to go from the hot to the cold system. So I know the change of entropy in one heat. But when there's one heat, careful. Then there's one heat, I gain macroscopic information, because before I didn't know what was going to happen. And after I know which one has happened. So the agent here is choosing, is creating information, is creating macroscopic information, right? When I go left or life, I choose, I am generating information. Where does information, how can I generate information? I mean, information cannot be created from nothing. Well, it's not created from nothing. It's created by eating up the negative entropy that was assumed in the past, from the past hypothesis. And the information here is a number, in the Shannon sense, is a number, is the log base 2 of the number of possible alternatives. That's Shannon definition of information. So this information here can only be fed by the growth of entropy, and which gives me an inequality between the information, the number of choices I can distinguish, and a quantity which is purely in terms of thermodynamical properties of the system. And I think this is absolutely fantastic, because out of pure thermodynamic, I get an expression about of the amount of information that an agent can produce. And if you want to, I mean, I'm not going to discuss this formula in detail, but there's a super simple limit in which you see what's going on. Suppose you branch between two alternatives, go yes or no, and you take a limit in which the collision is extremely rare. Then this inequality here reduces to the last inequality in the slide, which says that the temperature difference times the heat capacity, which is essentially the energy that excites the pendulum, must be larger than the thermal fluctuations, of course, which is pretty obvious. So there's nothing deeply new here. If not this idea, which I find fantastic, that the information generated by choosing by the agent is exactly the eating up of the negative information, of the information which is in negative entropy. So from a physicist's perspective, we understand exactly what is going on when there is a choice. Agency is a physical mechanism that transforms low entropy into information. And this, opened the door to say, well, easy. Biology is all about information. Culture is about information. Me talking to you is about information right now. Where does this information come from? It all comes from the low entropy, the free energy that feeds these processes. I'm gonna stop here for this first part and sort of bring home a number of ideas. First of all, that the openness of the future, freedom of choice, if you want, in the macroscopic world, it's perfectly compatible with physics. In fact, is dictated by physics, okay? And it's a feature of the macrophysics, which means that all the corresponding aspects of consciousness are grounded into physics, and they are telling us that two things. One, that the information that the macroscopic world can deal with are rooted into the past low entropy, and more importantly, that these phenomena are macroscopic phenomena. So they are a description of the world grounded in ignoring small microscopic variables, which takes us to a way of thinking about consciousness as a very average phenomenon, which is pure Spinoza. I mean, it's fantastic how the picture of mental world in Spinoza is implemented by modern science. I'll go ahead. Time is flying. Meaning. I'm talking about meaning. That will be a little bit shorter, and then I'll spend a little bit of time on quantum theory. So meaning is a characteristic feature of mental activity. We use the word meaning with a variety of meanings, if I may. So I'm not going to define it. I just define it as what the variety of things we intend, we mean when we use this word. A general aspect of meaning is that it's intentional in the sense of Brentani. It refers to something else, right? The word cat means a cat. The sound cat has to do with the animal. A sign, a street sign means something because it indicates there is a left turn up there, and so on. And meaning is relevant, namely, it's not just it refers to something else, but it's meaningful. Okay, it has importance for the subject in some sense. Now, why I'm interested in meaning? Because it's one of the hardest thing to think about for a physicist. If you have a physicalist picture of the world, prima facie, again, it seems that everything that has to do with meaning escapes it. And prima facie, also emotions seem to say rationality and aims, but then all these things seem to be not so hard to understand. If you work enough, you understand conceptually how all these other aspects of mentality, of mental world, can be connected to the physical world, but meaning seemed too hard. So that's why I was very interested in meaning. And I got this flash. In fact, I got the idea listening to David Wolpert talking at one of the FQXI meetings. And as a physicist, I realized that there was a very remarkable point he was making, and which can be very general, which is the following. Let me think in terms of a physicist. There is something that physicists know very well, which is the physical correlations. Shannon calls it relative information, and I've called it relative information in my papers. But people constantly got confused because information is such a word which is used in different meanings that that people say, oh, but information is already mental. It's a complicated stuff. So just think in terms of physical correlation. Physical correlation is a purely physical notion. It's the fact that you have two variables, A and B, and there is some physical fact such that the value of A and the value of B are correlated, okay? So technically, the number of possible states of the A-B couple is less than the product of the number of states in which A can be times the number of states in which B can be. If you have a pencil and you have a point of the pencil, the end of the pencil, the point can point north of south, the end can point north of south. So the point can be in two positions, the end can be in two positions, so you can have four positions. No, you cannot have four positions. You cannot just two, because if one point north, the other point two. There's correlations, okay? So this is a correlation, and there's an analogous information if you talk in terms of probability, which is the probability distribution of the couple AB is not the product of the distribution of A and distribution of B, which are the marginal of the coupled probability distribution when you fix A and B. All right, so this is correlation, it's purely physics, and of course nothing to do with meaning so far. Then there's another notion, which is a physical notion, which we get out from the Darwinian clarity about the physical ground of biological evolution, which is the following. There is a notion of utility, of relevance, which comes from evolution theory, which is the following. If we have organisms, physical systems that reproduce and survive and reproduce, if they have features such that the survival and reproduction is enhanced, then we can say that these features are relevant and useful for the reproduction and the evolution of and the survival and the reproduction and the flourishing of this kind of organism. So in other words, the Darwinian sort of turning around between what is cause of what, so exchanging the final cause with an efficient cause, allows us to give a physical sense, the purely physical sense. In fact, we can use it for talking about physical systems, a notion of utility, a notion of relevance, which is grounded in physics, because there's nothing that goes outside physics in the Darwinian story. All right, again, no meaning here. But, and this is the point, if you take these two notions, physical correlation and biological relevance, together, then you get something which we already would call meaning, okay? So again, we use meaning in a variety of contexts, but this is a context in which we definitely would use meaning. Namely, relative information is meaningful in the common sense of meaningful. And David Wolpert had a little sort of fable to illustrate that, which is following. Suppose there's a rock falling on from a mountain over you, and you move. Okay, why you move is clear. It's not hard to understand, because we are my ancestors. Those who didn't move in that situation are dead, and I'm the descendant of those who moved. Right, but in order to move, I have to know that the rock falls on me. So there should be some correlation, physical correlation in the previous sense, between something in my brain and the rock. And of course there is, because we have eyes and we have concept something in our brain that knows about what's there. But this is meaningful in the sense that if I take the same situation and imagine of cutting this correlation, of disconnecting the correlation between what is in my brain, the falling and the rock falling down, my survival probability would go down because I would be crushed. Okay. So therefore, there's a notion of a correlation, which is meaningful for me, enormously meaningful in that case, the correlation between what is in my mind and the rock. So there are all sorts of correlations between my body and the outside, but those are meaningful. So remarkably, out of pure physics, we see a notion of meaning coming out. And of course, then, biology, evolution has worked on that. And then we have a much richer notion of meaning, which comes when you fold in the complexity of our brain and all what happened in our brain, and then society, and then culture, and so on and so forth. But the point is that there's clearly a continuity that you can go from physics out to mental. For the six, last point, quantum theory. I still have not much, but some minutes, so I'm going to use it. So third point, does quantum theory say something useful for consciousness? Let me say some obvious things that I guess you all know. First of all, the brain is, of course, a quantum system, because all systems are quantum system. Without quantum systems, you wouldn't even have stability of the atoms. You wouldn't have van der Waals forces. So of course, quantum theory is part of the story here. However, it's part of the story in the same sense in which it's a part of the story when you understand the working of my car, which is atoms are stable because of quantum system. There's nothing specifically that I know in quantum system that helps us directly to understand the specificity of anything related to consciousness. In fact, the standard argument is that the brain operates at room temperature. It's an extremely strongly decoherent environment that erases interference effect. So we're deeply into the classical limit here. There's nothing quantum that you see. Of course, I've been following the various idea, nanotubules or whatever, in which trying to actually use the specific quantum phenomena to connect it to consciousness. I'm not convinced at all. I don't see anything coming out. I may be wrong, it's open, but that's my understanding so far. So let me brush apart all those attempts and just consider quantum theory in general. And here I think that there's a point. And the point is the following. Quantum theory is not directly relevant for understanding the brain. However, quantum theory is a deep way of changing what we mean by doing physics. It changes the nature of matter, our understanding of the nature of matter dramatically. And in particular, one aspect, or I would say the key aspect of quantum theory is contextuality in the sense of Bohr. So properties of a system are not just property of this system, are relative to the system, to the other system, the first system is interacting with. This is explicit in a number of interpretations of quantum mechanics. It's explicit in many worlds. It's particularly explicit in relational interpretation, which is the one on which I've worked and which I like and love. I'll say just a word about it in a moment, which means that the attribution of property to a system are relative to another system, right? An electron has position with respect to an apparatus that measures position, has momentum with respect to an apparatus that measures a momentum. It doesn't have a position and momentum by itself. But this means that physics ultimately is in the first person perspective, not in the third person perspective. This means that physics is about how a system affects another system. So it's about one system sees the other, in a sense. This, I believe, is the key discovery of quantum mechanics. It changes our way of describing the physical world. But if this is so, this observation demolishes the main argument, which is the one you find over and over again for saying that consciousness escapes the physical description of the world. The main argument being that the subjective experience is something in the first person while physics is always in the third person. That's not true. Physics is always in the first person if you fold quantum mechanics in. So let me repeat this point the key point about the relationality in physics and in quantum mechanics. Remember Bohr. Bohr characterized quantum mechanics by saying that the property of quantum systems in the lab cannot do, to talk about the property of quantum systems in the lab, we cannot avoid talking about the specific measurement apparatus used to measure that quantum system. That was 100 years ago, when the only quantum mechanical phenomena considered were in a lab with a physicist and measurement apparatus. 100 years later, we know that quantum mechanics is not about measurement apparatus and labs, it's about everything. Okay, and quantum mechanics, and a neutron star is quantum mechanical galaxy, it's quantum mechanics, everything is quantum mechanical. So quantum mechanics has nothing to do with labs and measurement apparatus, it has to do about nature and the way nature works. So Bohr observation, rephrased 100 years later, is that the property of any system are only relative to any other system which is interacting with it. And that's somehow particularly explicit in the relational interpretation of quantum mechanics, but as I said, it's implicit in other interpretations as well. Which means that in classical physics, we have this idea that the physics is about matter, which is big chunks of stuff which have properties. But that's not physics in the 21st century. Physics is how systems affect one another. So the physical description of the world is a description of a relation, not of things. And I come to the key point. The hard problem of consciousness is and this is somehow the rival point of all this discussion. The hard problem of consciousness is the intuition that there is a contradiction, an incompatibility between a notion of the subject, of the subjective view of the world, of the subjective experience of the world, the I, which is an irreducible unitary thing which has subjective experience, and matter, which exists in itself, incapable of subjectivity. It is obviously matter incapable of subjectivity. Hence, the I cannot be made of matter. That's the bottom line of all the arguments for the existence of hard problem of consciousness. And that's wrong, because both terms of this contradiction, both the I and matter, okay, are notions which are contradicted by the current physics. They're a result of a wrong metaphysics, where the wrong metaphysics is wrong because it's contradicted by current physics. Why? Because the I, as I argued in the first part, is not an irreducible unitary thing. It's a macroscopic description of a complex set of phenomena. It's a macroscopic phenomena. So it's made by a lot of other stuff, so to say. There's nothing irreducible about it. And more importantly, I would say far more importantly, matter itself is contextual. It exists only in interactions, hence in relations. So hence a subjectivity, which is the core of the intuition, doesn't, once again, I'm not going toward panpsychism in any sense. I don't think an electron has subjectivity. Subjectivity is a complex phenomenon, once again, that requires neurons, requires stuff. We have it, probably octopus have it, I don't know. But there is nothing a priori impossible to happen in the fact that a lot of relations together macroscopically can describe in terms of subjective experience. So nothing prevents complex subjective experience to be a specific form of combination of physical relations. Okay, that is what I wanted to do. I have this slide, which just the point here. Consciousness, I think, is a very poorly understood complex physical phenomenon, and I'm following with enormous interest the people who specifically work on it and construct beautiful pieces, models for understanding it, both mathematical, conceptual, experimental brain and so on and so forth, I see no as a physicist, I see no indication whatsoever that it could not be accounted in terms of the known physical laws, like we do in chemistry or astronomy, and of course developing specific concepts, like chemical bond is fundamental for understanding chemistry, but it doesn't go out our fundamental physics. I summarize. That's my summary. First of all, I repeat the last sentence. The consciousness is a purely understood complex physical phenomenon. I see no indication that it cannot be accountable in terms of known physical laws. It's a macroscopic phenomenon. We should never forget that. Otherwise, we don't understand it. Otherwise, we don't understand how it could be time-oriented. And it's not a single thing. It's a process happening in terms of something else. Second point, I describe its time orientation, which it's a key argument for a physicist that shows it's a macroscopic phenomenon. It depends on a vast number of degrees of freedom. I did not talk about my work on memory and traces, but I just give you the outcome here. The past is fixed because there are traces because of low entropy and long-term memorization times. And I sketched here the argument showing that the future is open exactly for the same reason. The macroscopic future is open every time we have lack of equilibrium between systems which have long-term memorization times. So agency is a physical mechanism that takes the low entropy information, sort of hidden, and brings it into the macro world. And this is a source, I believe, of the information of the macro world. The next point, which I went pretty fast, I think that the hard to understand notion of meaning in physicalist terms can be understood easily, can be grounded easily in combining the notion of relative information or physical correlation with the linear notion of relevance, which explain clearly why meaning is only a biological thing. There's no meaning in analysis. You need biology to make it. But biology is it's easily grounded into physics. And finally, no, not finally, it's semi-finally, quantum theory I think is not directly relevant from consciousness, but it does replace the metaphysics that makes it hard to think that consciousness is compatible with the physicalist view of the world, with a metaphysics of relations in which this hiatus it's much weaker. Once again, this is not an explanation. This is not a theory of consciousness. It's only an argument that says that the intuition against the possibility of a theory of consciousness grounded in current physics is it's a wrong intuition. And the last point, which is the one on which I closed, I think the traditional term of the dichotomy matter-mind, at the light of this sort of these high-level consciousness-related phenomena that I've discussed, seen from a perspective of physics, the traditional dichotomy is completely misleading. The world is not made by classical matter, nor by irreducible mind. It's a network of interacting system. That's a physical picture that's a picture that comes from physics today, at the light of our understanding of statistical mechanics, of quantum mechanics. And so the brain mind is just one particular system which we experience directly, and of course is still poorly understood. I've been talking for long, so let me stop here, and I'm happy to take questions.